handlers talk is going to be given by Daniel, who's going to tell us about compiling links effect handlers.
Yes. Thank you, Sam. And this is actually joint work with Sam, who's my advisor, and also Casey from University of Cambridge. Right, so this is about compiling links effect handlers to the OCaml backend, and I have been, for now, a PhD student for 2 weeks, so let's see how far I got. Right, okay, let's meet links. So I'll have a few code examples in this talk, and they will all be written out in links. So I just want to give a brief introduction, or sort of summary of what links is. So it's a functional programming language originally conceived for web programming. So I don't know if that's the reason, but it has a syntax that's similar to JavaScript. Yes, we have a linear type system. We have an effect system based on row polymorphism. And then about a year ago in my master's project, I implemented effect handlers for links. And not so important for this talk, but there are 3 backends for links. And in particular, what I have done in this work, I have replaced the interpreter with a compiler for effect handlers. So I'll give just a brief introduction to what effect handlers are and algebraic effects. So an algebraic effect is simply a collection of abstract operations, and one way to view non-determinism is a collection of a single operation called choose that returns you a Boolean. And using abstract operations, you can then start composing abstract computation that uses these operations. So for instance, coin toss, we can model that by say, if do choose, then heads, otherwise tails. So those are the 2 outcomes of at least a regular coin. So what might the type be of something like this in links? Well, as I told you, we have effect signatures or effect type system in links. So what we get here is we have a null-array function which returns me a toss. So the heads and tails are constructors of this type. And then on the arrow here, my effect signature or effect rows live. So here I'm saying that my computation toss may perform choose, and the choose operation has to return me a Boolean. And the E here is an effect variable or a row variable, in fact, so that kind of captures all the operations I haven't mentioned already. So this is just to say I can use this in a context of more operations. So what happens if we try and evaluate this computation? Well, it blows up and says unhandled operation choose, and that's obvious. I haven't given any semantics to choose yet. So let's try that. So how do we give semantics to choose? Well, we use an effect handler. So the idea of an effect handler is it instantiates these abstract operations. An effect handler in general can consist of multiple clauses, but in this example here I have a random interpretation of choose. It contains 2 clauses. Return clause, which is always mandatory, tells me how to handle the return value of the computation I'm handling. And then here the choose clause that tells me how to interpret the choose operation. And you might see here it exposes a parameter called resume. That is what Oleg called K in his talk. So that's simply a continuation of where the operation originally was invoked. So what I'm doing here is simply, I'm saying here, well, give me a random number between 0 and 1.0, and then if that's greater than 0.5, then I return true, otherwise I return false. So the type for this thing is the following here. So I expect as an input a computation that performs choose operation, and I return you then another computation in which choose has been instantiated. That's how you can read this funny syntax here, curly braces P curly brace. So it means it's polymorphic in whether it's present in further compositions of the computation. And now we can run it, and we get some random value out, like tails, for instance. Right, we can also do something else. We can do what I think Oleg also had this example with the sort of enumerating all the choices, or all the outcomes of all the choices we can make in a computation. So what we do here instead of applying the identity, we lift the return value to a singleton list, and then we simply visit or try both alternatives, the true and false alternative, and concatenate the results together. And here you have the results. You get heads and tails out from this computation. One final remark here is that we can also have a handler that itself is an abstract computation. So here's flip, I call this one. So what does this do? Well, it interprets choose by doing a choose. So this relies on having a parent handler around it to tell it how to do choose. And once it has this operation has been instantiated, we just take the negation of that, and then we return that to where the operation was initially invoked. And you might notice here now in the effect signature, choose appears fully present in both the input signature and in the output signature. And if you run that, then you get the composition here, all choices, flip, toss, then you get the opposite of what we had before. Now, you can classify handlers by how many times the continuations are used. So, for instance, an exception handler, I have an example here called maybe result, which I haven't shown you on the slides, but it's in the handout that's been handed out. The continuation is used 0 times, so that amounts to doing an exception handling. A linear handler is like random result or flip we saw in the previous slides. It only uses the continuation exactly once. And then multi-shot handlers may use them multiple times. Now, it's not all about tossing coins here. That would be quite silly. But I actually have a reconstruction of the concurrency model in links using handlers. And just to briefly sum it up, the concurrency model of links is a standard message passing model with type safe communication. And this construction uses about 5 handlers, and it's fairly non-trivial. So what we're interested in here is to try and make this abstraction and efficient and safe, and still, like, we want to retain modularity while doing this. So if you look at the compiler infrastructure, so I'm using the multi-core backend of OCaml. What I simply do is, since links is written in OCaml, I simply hook directly into the backend. I subvert the type checker and all the front end of OCaml, but this ought to be safe since I have my own type checker. And I map it into a language called Lambda, which is the first backend, IR of OCaml. And the reason for doing this is to get maximum flexibility. It allows me to explore the bytecode pipeline as well as the native pipeline, but at the moment I am only using the native pipeline. Right, so a little bit about multi-core OCaml here, which I think is important. So this was originally, they added the effect handlers to OCaml as an abstraction for concurrency, and in particular they provide an efficient implementation of linear handlers. And then the question is, how do we do multi-shot handlers, since links has these? Well, they have an explicit copying construct for these, so on demand you can clone your continuation. So for instance, here is the example again with all choices flip toss in links. It gives you us the tails, heads. Now the question is, what will OCaml give me for the same example if I do this sort of standard translation into OCaml? Well, it gives you an error. What happens here is that the on-demand copying of continuations is a rather fragile abstraction, and to understand that, it maybe helps to look a bit about how it's laid out at runtime. So what happens here is in OCaml, the handlers are implemented as heap managed stack data structures. So for instance, you will have the blue ones here supposed to be sort of my computation, my program stack here, and then I can install a handler on top of that. So for instance, we will have all choices as the outermost handler, or the bottom element in my stack, if you like. And I'll have flip as my second element in the stack with the handler on top here. And then my toss computation will run in yet another stack. So if you start out, when we start out evaluating this composition, we start out in the toss computation stack here, and at one point we will perform the choose operation. What then happens is we establish a link back to the stack, back to where actually it happened, so we can take the continuation and get back into the computation. And now we find ourselves in the flip handler, and it also performs choose. But now we get into the all choices, which is a multi-shot handler. So that means I have 2 links back to my flip handler, which is a linear handler, by the way, to emphasize that. So what happens here is I do the resume true here. I am back in the flip now, and here I take the negation of true, so I just resume false, and I'm now back in the toss computation. At one point, the toss computation will run to completion, and I will find myself back in the all choices handler. now you might begin to see what the problem is here. I have consumed the link I established to from H2 down to the task computation. So now I found myself here, what am I supposed to do? Well, it blows up. This is what happens. It's not as bad as it just explodes. You actually get an exception you can handle. But the problem is I haven't copied that continuation. So one way of doing this is to conservatively copy the continuation before use. So that means I always establish more links than I have the need for. Well, surely that can't be all that efficient. Rightly so, it's not very efficient. So here I have a small benchmark where I'm using the sort of concurrency implementation I have with handlers and links. So the red line here is the compiler running with the with handlers, the handler-based concurrency implementation, and the blue line here is the interpreter with its built-in implementation. I think it's based on LWT. And that seems to happen something around 80 processes when I get up that. It seems to be the interpreter seems to outperform my compiler, and that's definitely not what I wanted or had hoped for. And I was quite sure this had to do with the copying of, or there's too much copying with of continuations, because one observation you can make is that although I have 5 handlers in my concurrency implementation, all of them are linear. So I'm actually wasting a lot of space and time here copying. So the idea is to use the linear type system of links to track the linearity of handlers. That seems like a quite good idea. And does it work? Oh yes, it works. So here now the interpreter changed to a green line for some reason, but it's the same here. So the red one is still the handlers implementation without optimizations, and then the blue one down here is when I linearize my handlers, and you see I am able to recover a lot of performance. So, all good. Does this always work? Well, no, it doesn't always work. And the reason is a little bit subtle. So, we have these, we can see these sort of stacks of handlers when we compose them together. And the sort of idea I had was to use the effect system to propagate information about when I am in the context of a multi-shot handler. Because at that point, I need to promote my linear handlers to multi-shot handlers. But it only needs to happen for those that are in scope of the multi-shot handler. So this example here, H2 with a star here, the star denotes the multi-shot effect, if you like. So the boxes here are supposed to visualize that H1 is in the scope of H2, but H2 is not in this, sorry, but the bottom element, H2 cannot see the bottom element in the stack. So what I really want the translation to do is I wanted to translate, promote H1 to a multi-shot handler. This would be the ideal situation, and leave the bottom handler linear. So you could think of this as me having my concurrency implementation in the bottom of the stack, and then I will be running some multi-shot backtracking computation in the top of the stack. But sadly, because of the way the effect system works, this effect propagates all the way up through the stack, so I pay a huge price to use a multi-shot handler just once. So I lose all my performance once again. But the approach works when I only have linear handlers. So the sort of problem here is the scoping with when I have to promote my handlers, and I don't have an answer to this yet. So this is sort of very much work in progress. But I believe I have to somehow capture the type, the structure of the handler stack at type level. But exactly how to do this is not clear to me yet. And interestingly, there's also what happened there? There's also another example I would like to show you where this doesn't play out really well. So, for instance, in concurrent ML, we have, you can picture doing, having 2 channels and then doing a choice between them. And how might you do that? Well, you will then queue your continuation in both channels, and whoever gets around to serve your request first will then invoke the continuation and do whatever the program P is supposed to do. And then you would expect, for instance, if channel 2 consumes the continuation, you'll expect that the P turns into a null or to a nil, what we call a tombstone, and then channel H1 will have to handle this exception that will occur when it invokes the continuation next time. I think this is quite a regular pattern. But you might see the problem here again. So in the linear type system will now tell me, well, wait a minute, you are using the continuation multiple times, hence it cannot be linear, according to the type system, even though I want it to be linear, because I only intend it to be consumed by one of these channels. So what you end up with actually in my current system is this, and this is definitely not the semantics you want. You end up with actually having both channels able to resume two maybe slightly different programs, or exactly the same, depending on what I'm doing in P. So this is due to the linear type system of links not being expressive enough to capture this sort of use case. And I'm not completely sure yet either what is the right approach to solve this, although my advisor Sam tells me that might be a nice solution with linear type system we can play. So that means I might have to extend the linear type system of links. Right, and just to finish off, I just want to mention that I am definitely not the only one who has attempted to compile effect handlers. It's been done before. I think just the thing people have been doing mostly before has been to embed them in other languages, whereas I go directly down to the OCaml backend. And I believe actually I'm the first official user of the multi-core OCaml backend, and I'm using it to build another compiler. So to sum up, I think that algebraic effects and handlers provides a nice abstraction for effectful programming, and by using the OCaml backend I get mostly this native code generator for free, and I can sort of regard links now as an experimental front end to the OCaml language, so I'll be able to do stuff like to have this effect and type system and linear type system, so we'll be able to do experiments that are not currently maybe possible to do in OCaml. And then, of course, I think this type and effect directed optimization of handlers is necessary if you want them to capture, also to handle the common use cases. And I think it's promising, but there are, as I pointed out, a few challenges right now. And that's all. Thank you.
We've got plenty of time for questions.
Yes.
Gabriel?
So do you actually need multi-shot continuations in links?
Right, so will I need multi-shot continuations in links? That's a good question. Yes, so the way I see that, I think they're quite nice to have around, but you can sort of categorize into two use cases. So linear continuation tends to be about when you want to do control flow. So you can think of them as control flow operators, but multi-shot continuations are really nice when you're doing backtracking computations. And I haven't done this yet, so that's why I didn't mention it here, but I envision using them in transactions for the database, so to replay computations if I end up in a setting where I have to abort, for instance. And I think it will be a quite nice use case there. And then I would suffer the penalty of having everything becoming a multi-shot under my current system. And that's what I'm working on. I would like not to pay that price because it's not necessary. Yes.
So what extension to the linear type system?
Right, what extension to the linear type system do I need? So I'm stretching my knowledge on linear type systems here, but I believe I need the, so links does not have the width typing rule, and I believe that's the one I need. So that's then raises the question, should I implement it directly in the type system, or should I attempt some kind of encoding via first-class polymorphism? I don't know what the right thing to do there is yet, because links has first-class polymorphism, so one could maybe try that. Okay, well.
You mentioned that links can be thought of as a different content for OCaml.
Yes.
Can I mix links code and OCaml code in a single program?
Yes, indeed you can. Actually, the entire standard library in links I have typed in implementing OCaml, and then I just link against it at compile time. So yeah, indeed you can. So you can use modules and whatever from OCaml. And actually, my compiler produces code that's very similar to that of the OCaml compiler. Of course, there are some exceptions because links uses predominantly structural typing. So all my records I use row polymorphism for records also. So I don't know ahead of time what the layout of the records are. So I do something different there. Whereas in OCaml you have nominal typing and you know already, and you can just use use a box at runtime. So that's a few differences, but it's very close to what you will be doing.
More questions?
Continuing on this question, I think you can call OCaml from the link, but not the other way around. Otherwise, we would break the invariance that you were guaranteed within link.
So if I call, so I kind of call from OCaml into links. That's your question, and you say I will break my.
If you go this way, you could break the invariance, but that system of link is.
Right. Yes, I believe so. Yeah.
You would just crash.
Yes, I believe you can. Yeah, I think I could easily code up a case where it would crash horribly at runtime. Yes. Yeah, you're right.
So you can't recall safely across variables. You're not sure if the other side won't keep references, and you should roll back later. So you need linearity in OCaml as well.
Yeah, if you wanted to do the call from the OCaml world into the links world, yes, you would need that. Yes. Yeah, that would be necessary.
You could maybe insist that you were only allowed to do things linearly if you went via OCaml or something like that.
Yeah, that's something to think about.
Just add linear transfer to OCaml.
Yeah, I could do that next weekend. Yeah.
Any more questions? Okay, let's thank Daniel again.